Hello, everyone. Thanks for joining the webinar. I know today is a big day in India, big festival. Happy Dasara, happy Vijayadashami for all the participants from India. I know this festival represents the celebration of victory of good over evil, right over wrong. So it's nice that you're all able to join today. So this is our weekly webinar series on geoenvironmental engineering. I always say that you only, benefit by attending these webinars to know what's going on in geoenvironmental engineering, and you can get new ideas on doing the research, new research on this. So here is the schedule for our webinars until the end of this year. Today we have a very excellent presentation. And then next week, I just wanted to mention, we have a presentation on organic waste biorefineries. And this is going to be given by Professor Alessandra Polettini from University of Rome. I know her, and she and her team are working on this waste biorefineries. And it's a concept of waste management. So they basically want to extract high value products from organic waste. So they're doing a lot of interesting research on how to address waste heterogeneities, what are the technical and marketing constraints. So, and one thing I want to mention is that this is not the regular time. She has to teach a class. So we are having that webinar from noon to 1:30 p.m. Chicago time. So just I will send you reminders on that one. So if you are available during the time, please attend it. And past webinars have been recorded, and we have this YouTube channel. Please view those, if you're interested in. So today, this morning, I checked, we have 545 registrants for this webinar. So please mute your mic and switch off your video. So type your questions in the chat box at any time during the presentation. Our presenter will answer at the end of presentation. Thanks again for joining this webinar. So just a very brief introduction to our webinar presenter today. I know Dr. Craig Benson does not need any detailed introduction. Everybody working in geoenvironmental engineering area, they know him. I just, as a courtesy, I just want to briefly mention Dr. Craig Benson is the Hamilton Indoor Chair Professor in Engineering at the University of Virginia. I just understand that he just retired from that university. Prior to joining University of Virginia, Dr. Benson was the University of Wisconsin. He was at University of Wisconsin at Madison. There he was Wisconsin Distinguished Professor, Chair of the Department of Civil and Environmental Engineering, and he was also the Director of Sustainability Research, and he held other senior leadership positions there. Dr. Benson is a member of the U.S. National Academy of Engineering and the National Academy of Inventors. He's also a fellow of American Association for the Advancement of Sciences. Dr. Benson has over 3 decades of research, teaching, and consulting experience in broad geoenvironmental areas, such as containment of solid, hazardous, radioactive, and mining waste, beneficial use of industrial byproducts, and sustainable infrastructure. So with that very brief introduction, I welcome Dr. Benson to give the webinar. Thanks everyone again for joining. Again, and thanks to Dr. Craig Benson for giving this webinar.
Thank you, Krishna, for that kind introduction. I'm going to post my screen. Make sure I can get this going. Is that showing up fine on your side?
Yeah.
Great. I wanted to start off just to thank Krishna for this webinar series. It's been fantastic for a lot of people around the world, for the profession, and the tools that we've developed over the pandemic are being used in a really thoughtful, positive way through this webinar and many other things like it in the profession. So thank you, Krishna. I'm going to talk today about a really interesting project that actually just came to conclusion over the summer. And it deals with understanding the performance and the characteristics of radon barriers used at historical uranium mill tailings disposal facilities. And I'll talk through what those are and what that means. But very infrequently do we have opportunities to go back and evaluate how things really function relative to what we anticipated. We do lots of research about understanding mechanisms and properties and expectations about how things are going to work. And then we build them. We conduct quality assurance, quality control during construction. We measure properties. We demonstrate that we build something to specification. But not that often do we get a chance to go back 5 years, 10 years, 20 years, and examine whether what we built really still is the same as it is today, or has it changed and become something different? I've been fortunate largely through interactions with the U.S. Environmental Protection Agency, the U.S. Nuclear Regulatory Commission, and the U.S. Department of Energy to have access to large field sites around the United States, and actually globally. We've done a lot of this work, but with an interest in trying to understand, are the systems that we created in the past still behaving the same way today? And are they going to behave the same in the future? And are the engineering properties of the elements within them changing over time? And you'll see today really an example of alterations over time due to natural phenomena. This work was done, it's a collaborative work. My particular part was done through our CRESP consortium. CRESP is a U.S. Department of Energy consortium of 6 different universities that's focused on providing applied and translational research and technology transfer associated with environmental stewardship of the nation's responsibility associated with Cold War production. The United States has a long legacy of environmental impacts associated with the Cold War, and the U.S. Department of Energy has a commitment to remedy those impacts, and we conduct work for them to solve practical solutions. So this is done largely under their sponsorship. I'm going to talk today as the speaker, but this is actually a culmination of a lot of people contributing over the last 6 years. The PI is shown here in orange at the top. Bill Albright, a colleague of mine from DRI out in Reno, that Bill and I have worked together for a couple of decades on cover systems. Myself, Mark Furman, a recently retired radiochemist at Nuclear Regulatory Commission and former National Lab scientist. Bill Lykos, who's a geotechnical engineer and the department chairperson in civil and environmental engineering at University of Wisconsin. Jody Waugh, another person like Bill Albright that I've worked with for a couple decades on cover issues. Jody's a near retiring ecologist with the U.S. Department of Energy Legacy Management out of Grand Junction. And Morgan Williams, the younger member of our team, is also with U.S. DOE Legacy Management in Grand Junction. And Morgan is a soil scientist and a pedologist who recently came out of Cal Berkeley within the last couple of years. So we've got a very diverse team, all contributing with their different skill sets to this really interesting problem that we were able to work on for 6 years. We were the PIs, but as like many projects, the students that are involved do a lot of the work. Alex Mashad, who was a student at Wisconsin, who's a consultant at GEI these days. Nick Stefani, another student at Wisconsin who is now a consultant at Edgewater Resources. And Kuo Tian, who is a former PhD student of mine at Wisconsin and then a postdoc at UVA, is on the faculty at George Mason in the Washington, D.C. area. All these people contributed. I want to make sure they all get credit for it. But it's equally important to realize that these problems take different skill sets. And it's the intersection of the skill sets that really provides us with unique opportunity. So the title of my talk was about historical covers over uranium mill tailings disposal facilities. And some of us know a lot about uranium mill tailings. Other of you may be less familiar. And I thought just we take one slide and talk a little bit about what are mill tailings, where do they come from, and why do we need to manage them? We've used uranium and the byproducts of uranium as a tool for both defense and for energy production for the last 60 years. The source of that uranium is in uranium ore. It's in rock. And the key mineral within uranium ore today is called uranite. It's also historically called pitch blende. So we exhume rock. It's got uranium in it. That percentage of uranium is a very small fraction. It may be a few percent of the total mass of the rock. We take that, we excavate it out of the ground. I'm going to turn my laser pointer on. Great. We will grind it up into a fine particulate, and we will send it through a series of different pH solutions to extract the uranium and then alter the uranium into a usable form at a uranium mill. So we take the rock, we grind it up, and we essentially remove the small fraction of uranium that's in it, and we create something down here on the bottom called yellow cake. Yellow cake is uranium oxide. It is about 98% uranium, and that byproduct of milling then goes to the next phase of enrichment, where we would create a fuel rod or fuel or energy source for a weapon. The byproducts of it, which I mentioned, most of the material is not uranium. We generate an enormous amount of byproducts from production of uranium and just about any other type of metal that we extract from the earth. And the byproduct is called uranium mill tailings. It's the tailings, it's the waste product or the end of the production line. And historically, mill tailings were essentially a slurry coming out of the mill, and we would pump them out into a low area and had a relatively uncontrolled disposal source. Many of these facilities, as you can see this one in the lower right-hand corner, were in very remote locations. So the concern about the environment at the time, particularly when uranium production was beginning in the 50s and 60s in the United States, we had essentially large disposal units for mill tailings, which were unlined and exposed to the atmosphere, uncontrolled waste disposal sites. Today, we wouldn't be doing that, but that's what we did historically. And I don't criticize anybody for that behavior during the time. We just didn't know that this was something we needed to manage more carefully. In 1978, US Congress passed the Uranium Mill Tailings Radiation Control Act because we had discovered that we had created many of these disposal facilities which were uncontained, and they were having impacts on groundwater and on the atmosphere. So we were getting both air pollution and groundwater pollution. And UMTRCA, really a formative bill, has a whole series of requirements in it, but it required that we limit radon flux to the atmosphere. And we'll talk about what radon is, and we'll talk about what radon fluxes are. It limit water percolation of the waste, so gas out, water in, and limit groundwater contamination. We're doing that primarily by limiting water percolation in. Importantly, we needed to design these facilities to function for at least 1,000 years, at least 1,000 years. And after the first 100 years, have to function effectively with no maintenance. So that's a really challenging design goal for any engineering system, and including uranium mill tailings. You can imagine the effort that has to go into demonstrating that actually we can meet that requirement. But we're going to focus mainly on the cover. We've got a disposal facility full of uranium mill tailings that has a flux to groundwater, which we want to minimize, and a flux to the atmosphere of radon that we want to minimize as well, and water percolation in from the atmosphere that we want to control or minimize as well. So we're going to look at these two primary elements at the top, water percolation in and radon flux out, and how we do that with a cover over the uranium mill tailings. Well, let's talk a little bit about uranium and radon, just to put that in perspective, because I realize not everyone is familiar. Uranium itself is a mildly radioactive element. It is the core element that we mine for energy production. But itself, it's mildly radioactive. It decays very, very slowly. It's got a half-life of 4.5 billion years. So if we've got uranium mill tailings in a disposal facility, and we still have uranium in that mill tailings, that uranium will be present for 4.5 billion years at a minimum, right? Actually quite a bit longer, because the half-life is just 4.5 billion. But it degrades into other elements, and that degradation process has been going on for millennia. And as we step down through the decay chain, we get different radionuclides, some of which are more radioactive and have shorter half-lives. One in particular is radium. That's highly radioactive, and its daughter product is radon-222. And radium has a half-life of 1,600 years, long, but very short compared to uranium. Radon, on the other hand, has an extremely short half-life, 3.8 days. It's a short-lived element, but it's also highly radioactive. Importantly, radon is gaseous. And so as opposed to many of these other elements, which are metallic and solid, radon forms a gas. And many of us know that if you live in a home that's got bedrock, that's got some radionuclides in it, you have to test for radon. I test my basement for radon each and every year to confirm that my radon concentrations in my home are satisfactory. But of course, my home isn't built on a uranium mill tailings disposal facility. This is what one of these facilities look like. These are enormous facilities. This is one in Blue Water, New Mexico, near the Blue Water Mill, uranium mill. There's several disposal facilities at this site. We're going to talk about some data from this site in a bit. And the upper part of this figure is one of these facilities. It's 140 hectares. 140 hectares. That's an enormous facility. And you can see at this particular site, it's covered with a rock armor cover. A rock armor cover. And it stands out in all its surroundings. One of the things we think of with cover design today is trying to design things that are congruent with nature. This should, when you look at this photograph, you should notice immediately that this cover is distinctly different from the entire rest of the surroundings. So it's actually incongruent, and it will likely change significantly over time. That cover system that's over all these different elements are all a little different here. There's here in the lower right, I've got this one in the upper middle, and then there's another one over here. We'll talk about that as well. All of these have a cover profile on it that looks something to similar to what we see in the right here. It's a multi-layer cover. We've got the tailings at the bottom. And on top of the tailings, typically what's not shown here, we'll have a subgrade layer that's just a foundation to be able to build the rest of the cover. But then we'll have a low permeability radon barrier. That's what they're commonly called in the literature. And it's meant to have two functions. One, to control the ingress of water downward. That's the low permeability or low hydraulic conductivity, but also to control the egress of radon gas, which is generated from radium decaying to radon and radon being emitted from the tailings. So it's got to have two functions: water percolation down, hydraulic conductivity, radon emission up in the gas phase. That's a diffusivity problem. On top of that, we'll typically have a protection layer. Depending on when these were built, they may or may not have a protection layer. That design element came a little later. And then on top of that, many of these covers use a rock armor. That's not exclusive, but it is common, which was designed to be a riprap layer. And that riprap layer is just on top of a bedding layer. That's just a well-graded pea gravel size material beneath the riprap layer that the riprap beds in. The riprap layer was largely designed because erosion was considered the most destructive mechanism over the long term. We needed to manage erosion. The riprap layer itself had other unintended consequences. We'll see some of that. Now, how do these work? Well, I think a lot of us know about hydraulic conductivity. We don't all know about gas diffusion, but the factors that allow us to create low hydraulic conductivity also allow us to create low gas diffusivity, as we'll talk about in this slide. What I show here on this slide is a radon barrier here in the lower right-hand corner, and then looking at one small piece of it going over this blow up right here. If we can imagine, if we looked at it, we zoomed in, we would see that that section of the barrier has solids. It has pores between the solids, and it has some of those pores are filled with gas, some are filled with water. And for radon to make its way through that system, it needs to migrate through these pores, either through the water or through the air-filled components, and up from the base and then up to the top. That transport process is governed by Fick's law, which we show up here. And the key operative parameter is the diffusion coefficient, D, the gas diffusivity. The concentration gradient is essentially controlled. It's zero in the atmosphere and near zero. And down below in the tailings, it is whatever that particular tailings is emitting. Now, if we want to create a highly effective radon barrier, what we want to do is fill the pores with water, because the radon diffusion coefficient in water is about 10 to the minus 9 meters per square per second. Whereas in the gas phase or air, it's about 10 to the minus 5. So if I can fill those pores with water, I can create very restrictive pathways for gas diffusion. We do that by placing the barrier at high water contents, wet of the line of optimums, and compacting it so that we have small pores. So we'll have high dry unit weight, we'll compact it wet of the line of optimums, we'll get small pores, we'll get high water saturation. And in essence, we'll create very fine pores. We'll fill those pores with water, and fine pores tend to want to hold water and create a very low diffusion coefficient, and therefore a low diffusive flux. Those same ideas, as we know, work for hydraulic conductivity as well. Dave Daniel, I know you're on today. You may remember these slides from circa these photographs circa 1988 or so. We know from our basic principles of soil mechanics that when we compact clay materials that we use for hydraulic barriers or gas diffusion barriers that dry of the line of optimums, they tend to have large clods and large voids. And as we go drier to wetter, we go from a very open porous structure to a very fine material with no visible pores. And we can get that same effect by increasing the dry unit weight with a higher compactive effort. We can essentially just crush the pores, eliminate them by crushing the clods and eliminating the interclod pores. So the type of materials that are ideal for both hydraulic barriers and diffusion barriers, gas diffusion barriers, look like this or look like this. They're wet of the line of optimums. They have no visible pores, and those pores that are present, even though we can't see them, are filled almost with completely with water. Water saturation 90% or so. So the same things that create low hydraulic conductivity, which would get wet of the line of optimums, give us low gas diffusivity. That material that we create wet of the line of optimums is also highly vulnerable. It's wet, it tends to be softer, it tends to have very fine pores, and it tends to be very different from what is commonly found in nature. And so we're building a barrier that has engineering properties that are designed to meet certain goals, but it also has a challenge because it's vulnerable, because its state is not a natural state. And over time, nature will alter that barrier, as we'll see as we go through this presentation. And the challenge really is understanding how things evolve from the as-built condition to 1,000 years or so. We've been fortunate. We did studies early on with US DOE and Nuclear Regulatory Commission and EPA through the Alternative Cover Assessment Program, where we were studying the behavior of these systems 5 to 6 years out. This project we have today gets into the 20 to 30 years out period, giving a picture of where things might go out to the very long term at 1,000 years. One of the things that we use to look at this 1,000-year horizon is what we call a natural analog. I've been talking about how systems tend to evolve to a natural state. We often try to find a natural profile in the Earth's surface that mimics what we're building and is in the same environment. So we can study what it will look like in the very long term using that natural analog. And we'll see some of that as we go through today. So how will these systems change over centuries? Will the water percolation remain low? Will the radon flux be controlled? Do we have any information on that? It's interesting, until this study, we had no information about the long-term effectiveness in terms of radon flux. We do know from past studies, I talked about the ACAP study where we looked at covers that were 5 to 6 years out, that petagenesis or soil structure forming processes alter engineered barriers to a significant degree. We know that occurs. Petagenesis is inevitable in cover systems because they're near the surface, they're exposed, they're close to the atmosphere, they've got plant interactions, the natural system is in close proximity, wanting to alter them. Do we see those same type of issues, petagenic change, causing changes in the diffusion coefficients and diffusive fluxes? When we look at these longer term facilities, are we seeing facilities have been in operation for decades? Are we seeing the same changes that some of our other studies illustrated, changes in hydraulic properties? And then a question really that came out that we asked very later on is, as we were getting through the studies, can we actually design barriers that are more resilient and fit into a natural system more readily? And using a natural type of design approach. Well, we do know from some of our early work that these type of changes do occur in engineered barriers at uranium mill tailings disposal facilities. We were fortunate about 20 years ago, around 2000, to build a very large scale test facility at the Monticello Uranium Mill Tailings Disposal Facility in Monticello, Utah. It's in southern Utah. It's at a high elevation, about 8,000 feet. So it's both a desert environment and also a mountainous environment at the same time. When we were building the Monticello Uranium Mill Tailings Disposal Facility experiments, we had the opportunity to decommission some early experiments that were conducted at that site about a decade earlier. And that's what I'm going to show you in this slide. There were caisson experiments done at the Monticello facility where they built cover profiles within essentially a large metal caisson. They built a cover profile that they were anticipating several different variations to evaluate them, their hydrology. And when we were building our test facility at Monticello, we decommissioned these caisson lysimeters that were constructed at Monticello. And this is at Bill Albright on the left here, Bill's from DRI I mentioned, and Eric McDonald, who helped with this particular part of this previous study. He's a geomorphologist at DRI. But you can look through the cover system that was being evaluated early on at Monticello. We've got a surface layer, a fine textured material going down for water storage. We've got a biota barrier here that's essentially cobble with an infill of fine textured material. And way down at the bottom, you can't see very well, is the radon barrier, right down here at the very bottom. Well, we examined all these different components out of these caisson lysimeters. And one of the things that we did is examine the simulated radon barrier that was built at great depths, 2 meters deep. That radon barrier is put in, like we talked about, wet of the line of optimums, heavily compacted to have high water saturation and very fine pores. What did we see? This is the radon barrier, all right? We see two things that are evident. One, clearly we see cracks, right? These cracks weren't from us disassembling the lysimer. You can tell they've been there for some time. The other thing that we see is that there are roots within those cracks. Why are those roots there? Well, this is in a semi-arid environment where the vegetation has evolved to scavenge water. It will seek out and extract water that is available even at depth, 2 meters deep here. So the roots penetrate down through the profile. They find this wet, moist radon barrier. They embed in that barrier and they extract the water out to help to support transpiration. At the same time, as they're extracting the water, pore pressures are getting negative, suctions are increasing, and the soil shrinks and it cracks. And those cracks then become pathways for water flow, which then become more, additional sources for root water uptake in the future. So we know these are very real phenomena. The evolution of structure in these systems has been observed, is known. We actually saw this 20 plus years ago at Monticello when we were exhuming that. And we get structures like we've seen in the laboratory up here on the right. This is actually some lab experiments that Brian Albrecht and I did probably about 20 years ago with a highly plastic red clay from the Houston area. And down here in the lower right is a field sample of a similar type of material. You see a crack in it and you see a root within that crack as well. These structural features that develop in our highly compacted engineered barriers alter the hydraulic conductivity. In our ACAP study early on, we went back and we exhumed large samples, did field tests to evaluate the in-service saturated hydraulic conductivity and compared it to what we saw for the as-built condition. And if there was no change, we would expect the data to fall right along this 1-to-1 line that I've highlighted here in green. What you see is none of the data fit along that line, right? None of the data points. All of the in-service hydraulic conductivities are much, much higher than the as-built condition, at least 10 times and more like 100 times higher and sometimes 1,000 times higher. In fact, what nature does is alter that highly engineered barrier and puts it in a state that's conducive to the natural system. And what we do see is that the hydraulic conductivities of the barriers that have been in service tend to become fairly similar over time, regardless of where they were installed. And those hydraulic conductivities typically vary within a range of about 1.5 orders of magnitude. And we'll talk a bit more about that in a moment. The other thing that we see is the unsaturated hydraulic properties change as well. In these systems, both the saturated properties and the unsaturated hydraulic properties are altered, and they both influence the hydrology. Our percolation rate we focus primarily on saturated conductivity, but the unsaturated hydraulic properties are just as important for controlling water percolation in. And we know that as larger pores develop in the barrier system, we tend to have a soil water characteristic curve that's representative of a narrow distribution of fine pores evolve into a soil water characteristic curve that is representative of a much broader distribution of pores with a series of large pores grading all the way to finer pores. So we see an evolution in the soil water characteristic curve as well. Our early work on this was all documented in a new reg report. This is a really broadly used guidance document for engineering properties to use in performance assessments for low-level waste facilities and mill tailings disposal facilities. But a lot of that was documented back in 2011. And that report has been used extensively. But one of the issues with that report is that, and the data that I've showed you so far, is our early work was done on cover systems that had been in either test facilities or at full-scale covers, but they had been in service 5 or 6 years, relatively young compared to the timelines we're looking at. Of course, none of these facilities are anywhere near the hundreds of years or thousands of years type of performance that is ultimately of interest. But one of the criticisms of that work is it didn't reflect the long term. And many of those, the data sets that I just showed you were from facilities that were built as test facilities, not full-scale operating facilities. And that's what gave birth to our radon study that we finished most recently. One question was, do we see similar types of alterations that we saw in hydraulic properties at full-scale facilities? And if we see alterations in hydraulic properties, should we see alterations in gaseous diffusion as well? The diffusion properties should be altered as well. Is the diffusivity going to be altered in the same way the hydraulic properties are? And so we went to answer both of those questions. One, do we see that same type of behavior, the same type of alterations over time in hydraulic properties in full-scale facilities that have been operating for decades? And do we see alterations in gas diffusion that mimic what we saw for hydraulic properties in our earlier studies? We picked 4 different sites to do this work that ranged in climate and cover design. Falls City, Texas, which is in South Texas, Blue Water, New Mexico in the southwestern United States, Shirley Basin, South Wyoming, the west to Midwest, northern tier states, with cold weather, semi-arid, snow, freezing conditions, and contrasting Falls City, Texas, which is in South Texas, warm, humid, wet environment. And then Lakeview, Oregon, moving over to the semi-arid side of the coastal, western coastal United States as well. So 4 different facilities, different surface textures on the covers, as you can see here, different climates. We went to each of these sites and exhumed the covers in a series of test pits and examined both the hydraulic properties and radon diffusion as well. So goals of our work were, 1, to make radon flux measurements and to evaluate whether we were seeing radon fluxes that were different from what we measured in the as-built condition, to collect samples that we'd be able to document why those if there were alterations, why they were occurring. We also collected samples to look at hydraulic properties throughout the depth of the profile to evaluate whether we're seeing change in hydraulic properties. We did morphological studies to relate the changes in engineering properties to changes in structure in a quantitative way. And then perhaps equally important, if not more important, is that at each site, we found a natural analog. We found a similar profile in the Earth's surface that mimicked what was at our disposal facility, but had been in place for millennia. And we examined those analogs in much the same way we did the actual facilities to determine whether we were seeing similar types of alterations in the long term that we were seeing in our facilities. When we did our work, we used a bias sampling approach. And I think it's important to point that out. We didn't use a random sampling approach. We went out and looked for features where we would see the largest amount of pedogenic driven change. For example, this is at Blue Water, New Mexico. We did sampling underneath regions where we had woody vegetation, deep-rooted woody vegetation. It as an indicator of what the long-term state would be. This would be accelerated degradation due to the aggressive work of the woody vegetation. At these sites, we went, to back up just for 1 minute, as I'm indicated, at each site, we did bias sampling at the tailings facility itself, but we also selected an analog, and we did the same type of work and the natural analog that we did at our uranium mill tailings disposal facility. And this photograph actually is in eastern Wyoming, near the site in that region where we're examining the profile for a natural analog. And we'll come back to that. So at each one of our tailings disposal facilities, we exhumed test pits in the cover. Showing here with a little mini excavator, we're pulling off the surface layers and exposing the surface of the radon barrier below. On the radon barrier, put a series of flux chambers on the surface to measure the radon flux. We'd expose the surface of the radon barrier. We'd install a flux chamber on top and then we would measure what's called a so-called radon buildup. So we essentially put the chamber on top and it's closed. So it's got about essentially a no flux boundary condition at the top. And so the gas flows into that chamber, the concentration builds up, and as it builds up, because the concentration is increasing, the flux is actually slowing down. And we can use an analytical solution to evaluate the radon flux and the diffusivity from that what's so-called radon buildup curve, which I'll show you in a minute. We measured the radon concentrations in our flux chamber with an activated charcoal canister. That gave us a point measurement. But we did most of our work with an electronic radon detector, which is essentially just an alpha detector where we just pump gas out of the chamber through the radon detector and then back into the chamber, circulating it through and measuring the radon concentrations with the electronic radon detector. The RAD7, as I mentioned, it's an alpha detector, and it just measures alpha decay of radon. And so it's looking at alpha emissions, and then we can convert that to radon concentrations very specifically using the decay series. And we use these Durridge RAD7 radon monitors. This is an example of an activated carbon, not much different than what you might use in your basement. These were put into our chambers. Throughout our testing process, then sealed back up, sent to a lab and tested for us. This was done by Radon Testing Corporation of America. We did different size chambers to evaluate scale effects, thinking that if we had roots in our system and structural development that was occurring, that we should see scale effects in the diffusive flux, just like we might see in the hydraulic properties. We know hydraulic properties are highly scale dependent. We might expect the same thing to be true for diffusion. And for example, there's a couple of Shelby tubes that we collected from the field. You can see one, these are small 71 millimeter diameter samples. You can see a large root in it, small roots, some structure here. Clearly, even in this small sample, we see lots of heterogeneity. Another one over here on the right, which looks much more uniform. So we might expect very different properties depending on the sample that we collect and the size of that sample, in much the same way that we see with hydraulic conductivity, which I illustrate from a graph we made many, many years ago when we were studying hydraulic properties varying with scale and similar types of barriers. So we did tests at different scales. This is an example of tests that were being conducted. These actually were at our Falls City, Texas site. These are the large chambers here on the left and on the right. If some of you, if you've run sealed double ring infiltrometers that were made by Trautwein Soil Testing in the past, that's what these are. These are double ring infiltrometers, center ring, inner ring, that we've converted to a radon flux chamber. These are our large chambers, 1.5 meters on the side. These are medium-sized chambers, medium large chamber over here on the right, and then some small chambers here in this center right. And then we have some monitoring over here for health physics. We had a health physicist at each of our sites to ensure health and safety. This is a typical radon buildup curve that we get. The data represent radon concentrations measured with our electronic radon detector. It's building up and it starts to level out because as the concentration builds up in the chamber, it's a no flux condition. It's essentially creating a reduction in the concentration gradient and the diffusive flux. And we can analyze that data set and we can obtain the so-called initial slope from that, or the uninhibited radon flux, J naught, from that, fitting that data set with an analytical solution. We'll use these radon fluxes as I talk about that in a bit going forward, but they were obtained from analysis like this. So we fit the solution to the partial differential equation, this nice analytical solution, we fit it and get the radon flux. We did activated carbon measurements as well. I'm not going to talk about those so much. We're going to focus primarily on the electronic radon detector data. At the same time, we collected block samples. We did our samples at the top at first for radon flux with the radon flux chambers I just mentioned. Then we excavated down through the radon barrier, collecting large block samples for hydraulic properties testing back in the laboratory. So these are a block sample being exhumed, packed up in a protective ring, shipping back to the laboratory. Then here's one being trimmed back in the lab to a 300 millimeter diameter sample, and it's run in a large scale permeameter or a large scale pressure plate for unsaturated hydraulic properties. The other thing that we did as we went down through the profile is we did soil morphological surveys as well. This is Morgan Williams doing, as I mentioned, he's a soil scientist and a pedologist, and he did the soil morphological surveys. We'll talk just a little bit about that at the very end. And then at the very bottom, as we got through the radon barrier, we measured the surface flux off the existing tailings. So we were measuring emissions off the surface, the radon flux off the surface of the barrier, but also measuring the radon flux off the tailings below. So we had an ability to evaluate the efficacy of the barrier as well by comparing those two measurements. Let's look at some data. We'll talk about hydraulic properties first, then we'll talk about radon diffusion coefficients. I indicated we did an early study that for Nuclear Regulatory Commission, EPA and DOE, that created a guidance document, which I showed you. And that guidance document had recommended ranges of hydraulic properties to use in so-called performance assessments for uranium mill tailings disposal facility and low-level waste disposal facilities. Those recommendations had lower bounds and upper bounds on saturated hydraulic conductivity, which I illustrate here on these graphs. These are saturated conductivity plotted as a function of depth below ground surface. And in our guidance documents early on, we had a recommendation that for long-term conditions, an engineered fine textured soil barrier should be assumed to have a saturated conductivity between 10 to the minus 7 and about 5 times 10 to the minus 6 meters per second. That's quite a bit higher than what we install them in, but that's how petagenesis alters the property. And you may remember that range from the earlier graph I showed, that where I illustrated that regardless of where we installed the barrier, the hydraulic conductivities tended to fit into, over the long term, into a range. Well, these dashed lines represent the bounds that were reported in our original NUREG report. And one of the questions that we had was, are those bounds valid when we look at longer term facilities that have been operating for decades? We wanted to know as well, are the data we're collecting similar to what we're seeing in natural analogs? And are those natural analog data, are they consistent with the bounds that we've reported? And these are a couple examples. This is our Falls City site in Texas. You can see most of the data that we've collected. This is saturated conductivity of the low permeability radon barrier. Most of the data fit within those bounds originally recommended in the NUREG report were published in 2011. There's a couple lower ones at depth, but for the most part, they fit within that original set of bounds. And we see the same thing for blue water as well. Same type of behavior, a couple lower, but for the most part, they're all within the recommended range. Equally important, the analog data sets fit within there as well. The analog data fit within the bounds. These properties are quite a bit different from the as-built condition, which I show here with this yellow highlighting, less than 10 to the minus 9 meters per second. That's the as-built condition, intended condition, but it evolves, as I indicated, to this condition, which I show here in green. And that condition seems to be representative of the long-term state. At least our analog data would suggest that's the case. So the original recommendations in NUREG CR 7028 for hydraulic properties seem to be valid for most sites. This is Falls City Blue Water, these two sites, and we'll go and take a look at the other two, the Lakeview, Oregon site, which I mentioned a few slides back, similar type of data falling within the upper and lower bounds, but quite a bit different from the original condition over shown here in the left, but falling within the lower and upper bounds very clearly, in the analog following within those bounds as well. The analog, you'll probably notice on 2 of the sites so far, has been pretty close to the upper bound. The Shirley Basin site was a little different. This is in Wyoming. And at this site, the hydraulic conductivity had not evolved nearly as much. It was orders of magnitude below these lower and upper bounds. The data fall at least factor of 10, and in some cases, several orders of magnitude below. We had one right up in the range. And the analog at this site as well was quite a bit lower. And this is a very unique site built in the bentonite range in the United States. And that cover, the radon barrier, is effectively built out of bentonite. The entire barrier built out of bentonite, exhumed from a local bentonite source. And so it is different than the rest of the cover systems. And we might expect that Shirley Basin cover may be less permeable. It is a unique type of material and a unique environment. We looked at hydraulic properties as well. As I mentioned, we're focused on the next slide. We'll talk about the alpha parameter that talks about where the break in the curve occurs, and the N parameter, which defines the slope. Fine textured soils that have been compacted wet of the line of optimums tend to have a very narrow range of very fine pores. They'll have very low alpha and higher N to represent that pore state. We'll expect them to change as they get altered. And that's what we saw. Our original condition, our expectation from new reg CR 7028 down here in the lower left, and we're seeing many of our data up here in the upper right with much higher alpha and much higher KSAT. Falling in this range, consistent with what we saw in the new reg report. Now we have a much smaller data set for unsaturated hydraulic properties. Each one of these data points took about 8 months to measure. So it's an 8-month long test. We've actually got 10 more tests that are almost done. So in another few months, this graph will have be a bit more populated, and we'll be able to update it. But these tests are very long term. So the data set's small, but they are consistent with what we observe. Higher KSAT, larger alpha, consistent with the evolution of large pores within the profile. And we see the same thing with the N parameter as well. As a higher KSAT, we tend to get a smaller value for N, not a lot smaller, but smaller. As alpha goes up and KSAT goes up, we will tend to have a lower value for N, representing a broader range of pores as well. So again, consistent with what we observed historically from our new reg work on hydraulic properties. So that's the hydraulic side. Everything there pretty much was consistent with what we had observed before, except for the Shirley Basin site. Let's look at the radon fluxes for the last 10 minutes or so that we have. I've shown here box plots for the Falls City site. And I mentioned that we did bias sampling. So we sought out particular sites on the cover where we would, for example, have woody species or some other type of phenomena that might alter the cover more significantly and more rapidly than in other areas of the cover system. So it was biased towards kind of the worst case. But even under that condition, we look at the box plots of radon flux as built condition versus current, they're not a lot different. And in fact, our Umtrica flux limit of 0.74 becquerels per meter square second was met by nearly all the data. And actually by the Umtrica regulation, it's the average flux across the facility that has to meet that 0.74 limit. All of our sites met that limit, even though they had been in service for 20 or 30 years. So a very few points where we had higher fluxes. Those tended to be, though, in areas where we had distinct large pores from, for example, woody vegetation. I want to just caveat again that this was bias sampling. And so while it's a little bit higher, and as I report here, 4 times higher on average than the as-built condition, our sampling was biased. And the average in-service flux is probably actually lower. The key thing is still meeting the goals and not much different than historically. Here's some data from our Blue Water, New Mexico site. This is 21 years of service. A little higher here. There's more petagenesis at this site. We'll see some examples of this in a little bit later, but again, remembering it's bias sampling. About 10 times higher. Our box plot, the median of our box plot, or the center line, is about an order of magnitude higher flux, but still meeting the UMTRCA flux limit. So even though it's 21 years and it's evolved some, that flux is still within the regulatory requirement. That was very positive. While this site experienced much greater change, that it was still meeting the goals for radon emission control. And also noting earlier, I talked about how similar our analog properties were with our field measurements for hydraulic properties. We can probably make that inference for diffusive properties as well. Let's look at Shirley Basin, Wyoming. All right, this is a site that was built essentially out of a natural bentonite material. And we see essentially no change in the flux as built versus current, essentially identical, even though we did bias sampling, but we essentially got the same fluxes and well below the UMTRCA flux limit shown up here in orange. So again, we're meeting the flux goal, even though it's been in service for 20 years. In this site, really no change at all in the radon emission rate or the radon diffusivity. That's consistent with the hydraulic properties. Remember, at this site, the hydraulic properties had not been altered much either because it was built out of essentially a natural bentonite material. So what you've seen in each of these cases is that while there were, in some cases, no change in radon flux, in some cases, a modest change in radon flux, all of them still met the flux criterion, even in the case where we had a much larger one, a factor of 10 increase. We looked at other factors as well. So while that was all positive, we still want to understand what was affecting radon fluxes. And we looked at some of the things that we might be concerned about. So for example, we looked at scale effects, as I mentioned early on. And this graph is a little bit busy, but I want to talk you through it just a little bit. We're going to look at a couple other things in here as well. We're going to use this graph again. The purple symbols here are the flux measurements made directly on top of the tailings. So that's the waste, all right? Those are the highest fluxes. So one thing you see, regardless of scale, is that our measurements made on top of the barrier, which are all other points, green, blue, red, and orange with different size flux chambers, all those are below the flux emitted from the waste. So this barrier is effective in reducing the radon emission. It reduces the flux comparing the data, and I realize this is busy, but a factor of 10 or higher relative to what would be occurred from naturally exposed, or let's say uncovered uranium mill tailings. The other thing that we see here, if we look at this very carefully, is that there's no distinct scale effect. So for example, if there's a scale effect, we might consistently expect the larger chambers to give us larger fluxes because they would capture more large scale features. But what we see, for example, if we look at this one set of data here, this is the top deck and test pit 1 and our Falls City site. The green measurement has the lowest flux and the small chamber had the highest flux. So if there was a scale effect, those should be inverted. And if we could look through that same thing for each test pit at this site, and regardless of whether it was done on the top deck or done on the side slope, and we found no effect of scale on any of the diffusive properties. This surprised us, but was also very positive. That allowed us actually to commingle those data and analyze them in bulk. But there's no evidence of radon flux being scale dependent. We wanted to look too, did we see the specific impacts of factors like deep-rooted woody vegetation? So we picked sites, like I mentioned, like under a rabbit brush, where we would see deep rooted woody root structures down through the profile. You can see them all the way down through the radon barrier. Measured fluxes directly on top of those and went back and examined these profiles later on. This example here at the Blue Water site, we're going to go to one part of that site here and with the MTP upper cell, and we're going to compare data from two different test pits. These were two test pits that were in close proximity on the same test section. One was sparse, same test area. One was sparse vegetation used as a control, and then one directly beneath the salt bush, which had deep woody features associated with it. What we see is that the fluxes in the sparsely vegetated area are quite a bit lower. They're here relative to the fluxes underneath the salt bush. Probably 2 orders of magnitude lower. Why is that? Well, one, the salt bush, as it penetrates down through the profile, creates structure. And two, as we talked about early on with that example from Monticello, with the roots going down into the radon barrier, that plant is extracting water. And one of the things that we see is that if we look at water content profiles, underneath the salt bush, the water content is significantly lower in that region relative to the sparsely vegetated area. That's shown here in this graph at the right. The solid symbols, sparsely vegetated, the open symbols for salt bush. So the roots are drying it out. And what do we remember about diffusivity? Well, the water phase diffusivity is orders of magnitude lower than the gas phase. If we're removing the water, that means we have more gas-filled pores, higher diffusion coefficient. And so we saw very clearly that one, we got structure, but we also got changes in diffusive flux and diffusion coefficients, largely due to lower water contents from root water uptake. The converse of that, at the Blue Water site, in one of the cells, because it's built on tailings, and tailings are soft, compressible materials, that's one of those cells settled more in the middle because it was deeper. And it actually created a pond, a seasonal pond on top of the tailings facility. And so it would actually be covered with water in the spring season each year during snowmelt. And so in this case, we might expect, let's go in the areas of that facility that have been underneath the ponded condition. They're probably wetter and they probably have lower fluxes. So the converse to that. When we went and looked at that, we're going to, at the MTP lower cell at the Blue Water facility, TP1 here being the test pit 1 with fluxes that were in an area that was covered with water, and TP2, same part of that cell, but outside the ponded area, and we can see the fluxes are an order of magnitude higher. And that change at that site, again, largely due to water saturation. As I show here on the right, the filled symbols for TP2 and the open symbols for TP1. Wetter conditions, more water-filled pores, lower diffusion coefficient in the liquid phase, lower gas diffusivity overall, a factor of 10 lower. At this site, both of those were very low and well below the 0.74 becquerel per meter square second standard. So they both were satisfactory, but still the phenomena is true. Conditions that promote higher water saturation give us lower radon flux. One other example, do we see different cover types affecting the radon flux? Do they have similar types of behavior? So for example, this is a riprap covered side slope relative to a grass covered surface at the Falls City facility. The grassy surface on the slope having, on the top deck, having vegetation penetrating through, and the rock side slope being nearly devoid of vegetation, a few spots. And you can imagine that side slope, it's got very large pores. So when precipitation falls on top of it, it's going straight in and down. So very different types of conditions on the side slope versus the top deck. Does that give us a difference? Let's look at some of our data from Falls City. On the side slope, that's where we have the riprap. It's got a riprap surface. It has no vegetation to extend roots downward. and extract water. The diffusion coefficients on the side slope were very, very, very low, the lowest of the entire slope site. We go on the top deck, in contrast on the left side of my graph, top deck in an area with mesquite bush and grasses, we have much higher fluxes, a couple of orders of magnitude. One, we're getting root penetration, opening up the pores with structural change. Oh, you could apologize for bumping quickly ahead. But most of it done largely due to water contents. And that side slope, you can imagine, we're getting a different condition than we have on the top deck with wetter conditions on the side slope, as we see here. The side slope here is in open circles, the top deck in solid circles. And on the top deck where we have vegetation, it's pulling water out of the profile. It's drier. On the side slope, we have no vegetation to extract the water by root water uptake. And equally important, we have a very open surface which funnels water in. It's higher water content, higher water saturation, much lower hydraulic conductivity. That riprap acts like a mulch that retains water, increasing the water saturation. So we see a lot of these factors that affect both pedogenic development and water saturation. Essentially, the size of the pores and the amount of water in the pores alter the radon flux and correspondingly alter the radon diffusivity. One of the things that we've been working on recently is trying to relate these alterations to quantitative measures of soil structure development. This is really an evolving area, so I'm just going to show one brief slide on this, and then we'll wrap up. But we've, in each of those test pits I showed early on, we're doing a morphological survey to look at structure, and we can develop a soil morphological development score. It's an integrated measure of the different types of features that are observed in the test pit. And you can see that we are getting a relationship between a rough relationship between hydraulic conductivity and this soil morphological development score, with a higher score meaning more development, with the most permeable barrier materials having the greatest amount of morphological development, and the highest radon diffusion coefficients that we measured in the field being associated with areas that had the highest amount of structural development, as indicated by our soil morphological development score. We'll have more on that as it evolves a little bit later, but I thought I would show that to bring this together. So I had a little animation in there, but I'll just push on. So what are some of the practical conclusions? One, well, the hydraulic properties engineering barriers evolve while in service. We saw this from our early studies. Our full-scale evaluation of operating facilities confirm this. Structure develops due to pedogenic processes. They're more permeable, they retain less water, they have lower water saturation, largely due to the formation of structure within the profile, larger pores. This occurs not only at the very top surface, but down as deep as 2 meters. That was a question early on too. How deep does this penetration go? Well, we don't know how deep it goes, but we know at least it goes as deep as 2 meters. Our recommendations from 2011 in the new reg CR 7028 on hydraulic properties for use in a performance assessment, they're pretty reasonable. Our Shirley Basin site was at the low end and outside the range recommended in this earlier guidance document, but that using the recommendations in this guidance document at least would be conservative. So it provides reliable data sets for use in predictions for long-term performance. Our radon fluxes were not altered nearly as much as we saw from our hydraulic properties. We saw in some cases radon flux had increased by at most a factor of 10, and that was biased sampling. And in most cases, it was much smaller. In one case, no alteration in radon flux at all. So the processes, and that was governed largely by how much water was retained in the system. The water saturation was the most significant factor affecting the radon flux. Structure important too, but we saw consistently lower water saturations, higher radon fluxes. And so if we can do anything in terms of creating a more resilient system, create a system that retains water within that radon barrier to this degree that that's possible. That will make it more resilient over time. I've covered a lot of material in here today. If you're interested in reading more about this, there is a new reg coming out this fall that describes this the 6-year study. This was one gargantuan document with 6 different PIs. You can imagine just trying to put this together, but it will be available later this fall. It's in publication at Nuclear Regulatory Commission. So if you're interested in that, please look it up. And it is free. You can download it from the Adams document retrieval service at the Nuclear Regulatory Commission at nrc.gov. All right. Krishna, I went a little more than an hour and you told me I could do that. So
yeah. No problem. It's, thanks for covering a lot of details. Amazing research. I think, this shows, very comprehensive field evaluation of cover systems for radon. And I hope, the audience got, a lot of ideas from your research to conduct such field studies in addition to lab or modeling studies in our research project. So extremely, informative presentation. So do you want to look at chat box and answer some of the questions?
I will. Yeah, thanks. I've got a question from Rajul. Hope I pronounced that right. Any drawback of deep-rooted vegetation during construction and any environmental issues? Not so much during construction, because largely we're moving everything and eliminating all the historical structure that may have existed in the borrow materials, including root systems. But there are environmental issues that are significant. One thing we didn't talk about here, but when we have root structures that penetrate down in through the profile, and those roots are going down for a purpose. They're extracting water to support plant transpiration, and they bring up other nutrients for the plant with that transpiration process, root water uptake process. One of the things that happens in some cases is radionuclide uptake into the plant. And that plant species then may become the food source for an organism at the surface. So wildlife may eat that vegetation, and that vegetation may have radionuclide. So that is a significant concern. There's a corollary study that has been done by DOE Legacy Management out in New Mexico, demonstrating at least that tends to be, it does occur, but tends to be not particularly significant, but needs site-specific evaluation. So that to me is the most significant environmental issue. Yeah, Krishna.
So I will stop recording, Craig. So just to keep the length of the video reasonable, so we can continue answering the questions. Okay?
Sure.
Okay, thanks.
This one from Jyoti. I hope I